guys, it's me, David, and today's video will be on mole conversions.
So welcome everyone. Today let's talk about mole conversions. Remember last time this idea that a mole is a unit of quantity. It's a huge number of things. A mole is Avogadro's number, the same way we call a dozen 12. A mole is 6.02 by 10 to the 23. And it's the number of atomic mass units that are in 1 gram. So here's some ideas we need to connect. One, that atoms and molecules are too small to count individually. We need to count them by weighing or other means. Also, we can use any units we like to count particles. We have to use big units because there's lots of them. And finally, the chemical reactions occur in these fixed ratios. Look at the combustion of propane here. You can see it's actually 5 oxygen molecules, 1 propane molecule that make 3 carbon dioxide and 4 waters. They could be single molecules or dozens, or perhaps it wouldn't be dozens. You might even be able to say they were thousands or hundreds or even moles. So 1 mole of propane, 5 moles of oxygen, and so on. So anyway, let's use the mole concept to connect the masses of samples to the number of particles. So here we have the moles of particles in the middle, and we can convert to and from a number of particles using Avogadro's number. We can convert to and from a mass of sample using the molar mass of the compound in grams per mole. We can convert back and forth to the volume of a gas at STP, which is 0 Celsius and 1 atmosphere. Now we use the standard molar volume of a gas, 22.4 liters. And in a little while, we'll learn about the volume and concentration of a solution. We can do some calculations and convert back and forth between these two. So later on, we'll also get the volume of gases N, number of moles, is PV over RT, but that'll come in the gases unit. So don't be too upset if you're not quite there yet. In any case, so these are the ideas. Let's use them. Here is a problem where there's 3.2 moles of carbon dioxide, and we want to know how many particles it is. Let's go back to our map here and see we've got moles. We want to go to particles. We'll use Avogadro's number to do it. So here's that relationship. In every 1 mole, there are 6.02 by 10 to the 23 particles. Check the units, they're right. And you get 1.93 by 10 to the 24 particles. Here's another example. We want to find out how many moles of carbon dioxide are in a 125 gram sample. We'll need the molar mass of carbon dioxide. We just calculate here as 44 grams per mole. And you can see we'll just use that here. There's 44 grams in 1 mole of carbon dioxide. And we wind up, we check the units with 2.84 moles of carbon dioxide particles. So we do have to be able to handle these molar mass calculations. Like carbon dioxide we just did was 44 grams per mole. If you look at here diphosphorus pentoxide, you see there's 2 phosphorus, and those are 31 apiece. And we'll need 5 oxygens at 16 apiece for a total of 142 grams per mole. Here is iron sulfate heptahydrate. This is a hydrated salt of iron sulfate. So you need the iron there and the sulfur, 4 oxygens, and of course 7 water molecules, which are themselves each 18. So if you add all this up, you get 277.8 grams per mole, or 277.9 I think, and that's called iron 2 sulfate heptahydrate. Here's another example. We've got 155 grams of carbon dioxide, and we want to vaporize this at 0 Celsius and 1 atmosphere. That is at STP. So the question is, what volume of carbon dioxide gas will this produce? In order to make sense of this, we have to start with 155 grams of carbon dioxide that we've got. And let's see here, we can go back to our map here. There's a mass of the sample, 155 grams. We want to get to the volume at STP. So we'll go from the mass to the number of moles using the molar mass of the compound. And then once we've got the number of moles of particles, we'll use the standard molar volume, 22.4 liter per mole, to get the volume of the gas. So there's our scheme. Let's see what it looks like when we apply it to our problem. Here we go, back to the problem. We'll use the molar mass, 44 grams we knew from before. Now we're in moles. And then we'll do that moles to liters conversion at STP, 22.4 liters per mole. This we call the standard molar volume of a gas. If you calculate all these things, checking the units first, it comes out properly. There's 78.9 liters of carbon dioxide gas at STP that's produced. Let's look at yield analysis now. We'll take that same mole map concept and connect 2 of them together in a balanced chemical reaction between reactants and products. We use the mole ratio in between. So let's see, for example, what happens when we try to do a problem where we take some known mass of a sample in the reactants, and we want to find out how many particles or products are made. So we'll use the molar mass to calculate the number of moles of particles in the reactants, then use the mole ratio from the balanced chemical reaction to get the moles of particles of products, and then use, in that scenario, the standard molar volume, Avogadro's number, to get the number of particles of the products. Anyway, that's the general idea. Thanks everyone, and we'll see you soon. Don't forget, of course, to have a look at our next 2 videos in this topic, and stay tuned for our next lesson in Chemistry 11, lesson number 12, gas density.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!